I'm Michele Scalatella, will be the moderator for the next two sessions. The next session will be about continuing about applications for MIPI specifications, and it will be about enabling simpler design with MIPI I3C in different end equipment applications. And the presentation will be given by Samina Chondri and Amit Shara. I hope I got your names correct. Samina is a system engineer at Texas Instruments in the interface business. She's responsible for product definition, product roadmap, and strategy for the I2C and I3C portfolio in the transceiver interface product line. While Amit is a system engineer at Texas Instruments in the sensing group and leads product definition of temperature sensors, including analog, digital, temperature sensors, and thermistors.
Hey, thanks everyone. Thanks, Michele, for the introduction. So in this presentation, we will be talking about brief motivation about I3C, and then covering some use cases, applications in different end equipments and markets, including servers, communications equipment, consumer electronics, industrial and automotive, and then highlighting some key attributes and features of I3C that enable simpler designs in these end equipment applications and use cases. So highlighting briefly what I3C is and what are the key attributes of this interface. I3C was developed by MIPI Alliance. It is basically an intelligent multi-featured interface, and it improves upon the attributes and features of traditional I2C and SPI interfaces. But in the end, it basically gives us a more unified, faster, cost-efficient, and high-performance interface. It is implemented using CMOS IOs and basically uses two wires to overall reduce the pin count, similar to I2C. And it also helps to reduce the number of signal paths between the components as well. The clock is always push-pull in I3C, and data is most of the time push-pull. That helps enable faster speeds, and it operates at low voltage of 1.2 to 3.3 volts. At 12.5 megahertz clock speed, it is over 12 times faster than legacy I2C interface. The STR mode of I3C is basically enhanced version of I2C, but I3C also supports higher data rate modes that add significant functionality, and they are designed to transfer more data rates at the same bus frequency. I3C also offers multi-controller and multi-drop capabilities, and it supports these standardized commands which enable bus management, configuration, and control. There is a feature called dynamic addressing in I3C that automatically assigns dynamic addresses to all I3C targets on the bus. But I2C devices, most of the I2C devices with static addresses can also be supported. So that helps with the backwards compatibility of I2C devices that can also operate on the I3C bus. We'll touch upon different advanced features of I3C throughout our presentation, mostly the target resets, in-band interrupt, hot join, etc. These advanced features basically enable easier adoption of I3C, and they also enable simpler and innovative designs in different end equipments and applications that go in different products like smartphones, wearables, systems in different industrial and automotive applications, etc. So let's go deeper into different applications and different end equipments. We'll start with some common applications on the server side. And the first application we are going to talk about is the server's bus switching. So what's a switch? In these applications, a switch or a protocol-aware switch is basically a target device which is controlled by the I3C bus, and it basically fans out the input I3C signals to a number of downstream channels or pairs. In this application, on the left-hand side, for example, we see two controllers and one downstream target. And this is a common application we see on the server side where an I3C MUX is basically used to communicate between a CPU and a baseboard management controller. So the two controllers, each of them can be selected as an active controller, which has the control of the target port as well as the I3C target device. And the downstream target device could be a DIM module or any I3C target that the controller wants to communicate with over the I3C MUX. In the second application over here, we have one I3C controller. The MUX is basically fanning out the input clock and data pair to two downstream target ports. And either of these target ports can be selected. This is an application where there are multiple target devices that have the same address, and an I3C MUX can be used to basically avoid the address conflict. By selecting the proper downstream channel by the I3C controller, the controller can communicate with more targets on the bus that have the same address. The features listed over here on the right-hand side basically make the designs simpler and more efficient in terms of cost, speed, lower pin count, etc. In these bus switching applications. The first one being target reset. I3C supports target reset, where the controller sends a specific target reset pattern to reset one device on the bus or multiple devices on the bus. And this is helpful in these applications where a device is unresponsive, and in order to avoid the deadlocks on the bus, the target reset pattern can be sent to the device to reset it. It also enables lower pin count, because now you don't need an extra dedicated wire to generate a hard reset on the device. It can be handled via the I3C protocol through this I3C target reset pattern. Another feature that is valuable in these kind of applications supported by I3C is in-band interrupt. The in-band interrupts in I3C, they are called in-band because they are handled via the I3C bus. It is very beneficial in terms of faster and efficient asynchronous data acquisition and event processing. No extra dedicated wire is needed. The target can basically take control of the SDA line and generate an interrupt that can be serviced by the controller. It helps significantly in overall reducing the footprint, because now you don't need an extra wire for the interrupt line. In these server bus switching applications that require faster speeds, the I3C SDR and HDR modes, they provide faster bus transactions, overall reducing the CPU cycles. Talking about another applications on the server side is a buffering application. So the applications on the server side, they mostly deal with higher bus capacitance issue, and MIPI I3C basically specifies bus loading of 50 picofarad or less. So in these kind of applications, an I3C buffer can basically be used to connect multiple I3C targets to the downstream bus. In this way, bus systems can be extended without any degradation to the performance, because the buffer is basically isolating the bus capacitance. And a common application of these I3C buffers is on the backplane, where the buffer is basically placed on the I/O peripheral card, and it connects multiple I3C devices on the card to the backplane safely upon a hot join event. If the I/O card was plugged in directly into the backplane, it would add all the capacitances of the backplane and I/O card and result in issues meeting the rise time and fall time requirements specified by the I3C protocol. If the I3C buffer is placed on the edge of the I/O card, it is going to isolate the bus capacitance and redrive the signal without any impact on the signal performance. A key feature supported by I3C in these kind of applications is hot join, which basically allows the targets to join the bus after it has already been configured. This feature significantly helps in improving the overall power management and energy savings by enabling subsystems so they can be selectively powered on and off, and they wake up only when they are needed. So this helps in significant energy savings. On I2C sides, a special feature needs to be added to support this kind of feature to minimize the disruptions that result because of the hot join event. So the hot join feature supported by I3C, it is ideal for I3C devices that are mounted on the same board, but they need to be depowered until needed. Or, for example, the use case that we covered, these I3C devices are mounted on a module or a board, and they need to be physically inserted after the I3C bus has already been configured.
So one of the other applications that have started coming up is in server sensing. So with the development of the DDR5 and higher data rate memory devices, uh, the configuration of each DIM card has now been moved from a system level to the DIM card level because of the large power consumption on the DRAM 5 memories. So as a result of this, a lot of components have been moved from the server chassis onto a DIM card, but the DIM card scalability still remains. So to be able to perform low latency operations to configure these memory cards for different speeds, I3C plays a very critical role in being able to not only get the configuration of the system, but also to configure the system and then perform runtime monitoring of the temperature, because with higher power comes higher temperature. So this is where the integrated interrupt management also plays a very important role, that, as highlighted, because if the temperature sensors signal that a particular DRAM in the chassis is heating up rapidly, it allows the application to quickly reduce the data rates so as to reduce the PMIC power consumption, or warn the host controller to offload some of the compute on that particular memory card. So as you can see on the right hand side, I2C speeds have been limiting. So with the scalability comes the fact that as the DRAM business grows and the and the speed requirements increase, I3C with the STR and HTR modes allow faster management and frequent accesses to each of the memory modules. Secondly, the in-band interrupt, which is now driven through the I3C bus STA pin, allows for a very seamless operation. In the past, an alert pin was required, but with the I3C bus, that requirement has gone away. And at the same time, the inefficient polling mechanism to check the status of some of the peripherals, I3C target peripherals, that no longer exists, because each device can now signal whether it has something for the host to process.
All right. Another application we want to talk about is on the communications equipment side. In this application example, you see different type of optical modules. These are small form factor pluggable modules. The most common one being the quad small form factor pluggable module, the CFP, and then the octal small form factor pluggable modules. All of these modules, they feature 3.3 volt IO interfaces at the connector side. And inside the optical module, there is an ASIC and a micro that communicates across these interfaces. Now, these ASICs or microcontrollers inside these modules, more future-looking ASICs are moving towards smaller geometries, lower voltage nodes, higher speeds, and smaller footprint. The octal small form factor pluggable modules highlighted on the top over here, it basically supports high data rates up to 400 gigabits per second with 8 lanes. And it supports I2C interface as the common interface, but it also has an optional support for I3C SDR mode as well that supports 12.5 megahertz clock speed. So these type of optical modules, when they interface with the connector, they require an I3C level shifter to translate the signals from 3.3 volt down to 1.2 volt or 1.8 volt, depending on what are the IO voltages these ASICs are going to support. And here I3C key features, they support in the sense that as highlighted in the previous example, I2C speeds are becoming more limiting as the amount of data increases on the bus. I3C STR mode with these in these modules, they are basically going to support higher data rates on the bus, allows faster management interactions, and especially if you want to program these modules at a faster data rate, I3C high speeds become more efficient compared to I2C. And also to support high speed telemetry, I3C STR mode is preferred compared to I2C. Since these modules, they also support the legacy I2C interfaces, the backwards compatibility of I3C to support multiple I2C devices as long as they support the backwards compatibility requirement in terms of 1 megahertz support, no clock stretching, and 50 nanosecond spike filter. They can coexist on the same bus. And when the controller needs to switch to higher data rates for communication at higher speeds, it can communicate at SDR modes with the I3C devices.
Going into the consumer electronics and automotive market, I3C is definitely a, a bus that is going to proliferate. In the consumer electronics market, one of the key requirements is on energy. So with the SCL now being push-pull and that the system can start directly in I3C mode, allows for a system that is built purely of I3C devices to not only increase the communication speed, but also require the time for which the target sensors are in active condition. So the sensor can now play a better part in managing the overall battery life by being in a standby state with lesser amount of communication for the same amount of data. Similarly, in the automotive market with the I/O expander, the host control can now expand its I/O to multiple peripherals or target devices. And this also helps in better managing the speed and energy because with the push-pull bus versus an open drain bus, there is no current drain to the ground when the output drivers are switched. So overall, the bus management not only becomes faster, energy efficient, but also simpler. The other features like the in-band interrupt reduces the GPIO, which is a very important consideration in the board layout because having the GPIO while MCUs can have the controllers can have those GPIOs, the routing on extremely small form factor applications like wearables becomes a major concern. So now with the in-band interrupt, the additional GPIOs can be eliminated, allowing the MCUs to be much smaller while getting the same amount of data. At the same time, the reduced system cost is also realized because now we don't have to increase the number of IOs just to be able to communicate or get interrupts from mission critical devices or target devices on the bus. Lastly, in the industrial application, especially in the test and measurement applications, we are seeing an increased requirement on throughput because with the scalability of these systems, there is a requirement that more and more integration of sensors happen in these systems. So depending upon the kind of application they are being used for, there could be tens of temp sensors or optical sensors and humidity sensors to be able to control the process. And slower data rate basically limits the capabilities of the system. So based on an application's requirement, whether temp has to be monitored or humidity has to be monitored, now the systems can actually prioritize through dynamic address allocation which devices for a particular kind of test or test equipment, which devices generate the interrupt and get the highest priority. So for example, when doing a high temperature test, the temp sensors are involved more, whereas when doing something like a Haas test, humidity sensors require to maintain the chamber at a particular temperature, particular humidity condition. So the dynamic address allocation along with the in-band interrupt plays a critical role there. At the same time, safety systems also requires the host to have dedicated interrupt lines and run prioritizations, which can create more problems because conflicting interrupts from sensors can create a condition where nested interrupts, specifically on low-end microcontrollers, can cause them to miss out on critical events. So with the in-band interrupt, that is also mitigated because the host will receive only the one which it has allowed priority for. So the software on the host side becomes much simpler. As we talked about earlier, that there is an increased throughput requirement. The SDR and the HDR raw dates of 12.5 and 25 Mbps also allows the host to query data with low latencies on devices which are not on priority but definitely need to be serviced. So, in summary, the MIPI I3C bus it allows applications to leverage some of the standardized capabilities to expand and scale. These are in the form of its CCC commands. Simultaneously, the two-pin configuration with the integrated in-band interrupt and hot join indication now reduces the requirement on the host controllers to scale because what is now scaling is not the controller itself but the firmware. So if the firmware with a standardized stack is also there, it allows the application to scale over a period of time. Lastly, reduction in energy consumption from the faster bus traffic not only means lesser energy consumed during the bus traffic, but also enables green technologies, primarily due to the fact that the system can stay in idle state or the bus can stay in an idle state for longer times. And this enables this market to grow beyond the industrial and automotive sectors.
All right, this is just highlighting some application briefs. The first one, the next generation serial communication, basically highlights general applications and general introduction about I3C, the different end equipments we covered, and briefly highlighting the key features that enable simpler designs in these applications. And then the second application brief specifically talks about thermal sensing performing with the I3C bus.
Okay, well, thank you. I think this was a really amazing presentation. Thank you, Samina and Amit. I think we really presented a very broad field of applications, which shows, that this the capability of this standard is really truly amazing. I hope the people that were listening had the same impression that I did. I think you mentioned this already regarding power and in consumer and so on. I mean, how does I3C help with the applications that have stringent power restrictions? We're thinking mostly wearables, IoT, portable devices, battery-based, and so on.
Sure. It means in terms of the I3C, if you look I3C versus the I2C, I2C requires an external pull-up resistor, which is permanently there on the bus. So any device which is driving the bus, when tri-stating the bus, there is a leakage current involved, but when it actively drives a zero, there is a path from the supply via the resistor to the ground, which actually causes current drain on your application. Secondly, the I2C speeds are not much higher. So that means that the low time, that is when these drivers are on, is extremely long. And along with clock stretching, particularly the current drain on the systems is higher. On the other hand, I3C has an integrated pull-up into the host controller. And with the push-pull IOs, it means that there is no direct path to ground. It's only the leakage current. Secondly, this pull-up resistor is also switched. That is, this pull-up resistor is not permanently present, but it is actively switched by the host. So during the time when the I2C frame is involved, that's the only time when this pull-up resistor remains active, while allowing to be kind of in a passive mode during the regular operation in I3C.
And I can add two more things to it. I3C HDR modes, because they are high data rate modes, so you can put the CPU back to sleep sooner and it's faster. The second one we highlighted is the hot join, where you can put the targets to sleep and they wake up only when needed. So that also helps with significant energy savings for the applications.
Okay, thanks. I think that was, but talking about the hot join, how is the in-band interrupt different from hot join? You also mentioned that you can do also data acquisition with the in-band interrupt. It seems similar, but they probably serve a different purpose. If you could elaborate a bit on that.
Yeah, they have the same pattern, but hot join, they have this specific predefined reserved address for I3C, which already has a high priority. So when the targets, they join the bus via hot join, they send this reserved predefined high priority address, which is recognized by the controller. And then the controller acknowledging that address, it initiates the dynamic address assignment procedure for these hot joining targets. And secondly, in in-band interrupt, the in-band interrupt is followed by this mandatory data byte. That mandatory data byte is not required in hot join devices. So those are the two main differences between hot join and in-band interrupt.
Okay, thank you. We have a question regarding JEDEC. JEDEC added an in-band reset using timed pulse to prevent a hung device from holding up the bus or dropping communication. Is there a MIPI consideration to adopt an in-band reset mechanism that does not rely on a working target device? It's quite specific. This is not the application if you're... Okay.
Yeah, I mean, on the MIPI side, we do have the bus reset pattern, which is a separate pattern detection mechanism. So unlike the timed reset, where it completely depends upon whether the bus, where the controller is stuck and how the controller is designed, in case of the bus reset pattern mechanism, the pattern mechanism is completely different, which otherwise does not exist on the bus. So having a pattern to be able to soft reset the device or hard reset the device based on the on the target device design allows for a more seamless operation versus a timed reset. Specifically considering that with a bus reset with a pattern, you have a faster recovery versus a timed reset where the standardization, and it goes back to the previous question, between I2C and I3C. Some of the differences is that why wait for 50 milliseconds when the whole pattern can be executed in a millisecond or so, and the system can recover much faster.
Clear. Okay, thank you. It's probably time for just a couple more questions before the break. One question actually is for me. I saw your server bus switching slide. You show two switches. One is quite clear. The one on the left, where you had two controllers acting on a device. What is the benefit of using the MUX instead of having, for instance, main controller and a secondary controller, different voltage? I don't know what would be the main reason to have the switch rather than relying on, let's say, native I3C features.
Yeah, so I think one way to look at it could be a debug controller or a secondary controller where the active controller is basically, it is put to sleep and the secondary controller is monitoring everything as a debug controller. That's one kind of applications where an I3C MUX can be used. And the protocol stays the same. It is monitoring if there are any interrupts coming from the downstream target. So all those protocol-aware features, they still need to be supported, and I3C MUX can be used in that application.
Okay, clear. Thanks. Okay, I will suggest let's have the last question. And how does the I3C standardize bus management versus I2C? I2C has a number of bus management features.
Yes, so I2C primarily defines the physical layer and some of the higher layer functions, but pretty much every manufacturer or every device that exists in the market uses some different form of it. For example, how to start a conversion or whether to add a CRC to it. I3C kind of steps away from it and says, let's look at it holistically. What about enabling interrupts? Every device that exists today as an I2C device, you might have to end up writing to 3 or 4 different registers to enable the interrupt. Here you are globally enabling or disabling the interrupt through a CCC command, which is very well defined and listed as a mandatory command. So anybody that understands that, hey, I want this bus to stop interrupting me, the host controller issues the dissect command, and pretty much everybody shuts down. They don't have to go individually into every register map to be able to disable that.
Okay, clear. Yeah, thanks for the answer. Okay, unless you have any further comments, I would like to thank you again for the excellent presentation. I think this overview of I3C application was very, very valuable. And thanks again for people attending and to the speakers.
Thank you, everyone.
Thank you.